start the recording. All right, so here is the link for that. Let me publish this poll and then clear out the poll here. Let me go to the public chat and clear this out. Okay, so here is the link for this. All right, you just need that number. All right, so go ahead and get in there. This is what we did yesterday, energy systems. We had the 3 systems. Remember, we had the open system that the boundary can let heat and energy and as well as matter go out. We had a closed system where the boundary was covered, so we had a cover for the tap of the cap or on the bottle, but then the energy could be released. And then we had isolated systems which control everything. Nothing can get in and out. It's very hard to get that in that particular case. Hey, thanks for getting in there, Natalia. How about you, Tyler, Stephen, Lucas? You want to get in there, please? Kendall, Jabari, get in there. Thank you much. Cadence, get in there. Brennan, good morning, afternoon, get in there. Luna, get in there. We're gonna go to take a look. Okay, who's now they've put the code in as their name. Let me delete you here, and then you can. Oh shoot, cancel. Nope, moving too fast. All right, let you get in with your real name there. Okay. All right, let's get started. You can join in anytime. All right, so let's take a look at these questions here. All right, a system, remember, it's a collection of interacting parts separated by surfaces by a boundary. All right, right? So it's separated by a boundary. Collection of interacting parts used as a unit. So this would be what we'd be wanting here. First one on that. So first question is a collection of interacting parts. Let me kind of give a click on this thing. All right. Interacting parts separated from the surroundings by a boundary. All right. All right. All right. Thanks so much for getting in there. AJ is having trouble. Jabari is getting in there too. Hey, Jaina. What happened to you yesterday? You left. Did I not answer your question or something? And then you took off. You were mad at me? Hope not. Oh, good. Glad you weren't mad. Because I didn't see your question right away. Let's go to the next question. Oh, you're. All right, we got some more people in there. Good job, Ty. What type of energy system is this? So the 3 types, remember, are open, isolated, and closed. So you're going to click on all of those. Isolated, open, and closed, right? I'm going to click on all 3 because isolated keeps everything in the environment. Open lets heat and energy out of the environment as well as matter, like a boiling pot of water. And closed is like a chemical reaction we put a top on, right? All right. Did we get everybody there? Wow, that's cool. All right. All right. So this is an example of boundary that is closed. Okay. What is it? That's only getting in and out. And if you can take a look at this picture here, it shows only energy is getting in and out, right? So only energy is getting out in a closed system because we have a top on it, right? We have a top on it that keeps the material inside, but energy can kind of, because it's not insulated, can be taken out of the outside, right? All right. AJ, you and Jabari still having trouble with getting in there. Sorry that's happening. Hey, glad you're in there on time. It's better late than never, right? Especially if you have internet. All right, so a teapot boiling a stove is an example of, remember, it's got a top there, it's open, right? So it lets heat out, lets steam out, so that's matter. So that is an open system, right? Open system is what's happening here. All right. Okay. And sometimes quizzes just gives you trouble with logging in. It won't let you answer the question. So it depends on your internet speed. So I apologize for those people that can't get in there. All right. So what was this one here? We got 10 questions, or I think we have 10. Yep. All right. So a boiling pot of water with a sealed lid. It's not a closed, it's not an open system because we got a seal on it, right? And it's not isolated because we can feel heat coming out of it, right? So it's got to be a closed system. A closed system. Isolated, remember, no, you couldn't feel the heat coming out or the material. Open system would let the water boil and let it boil over. All right, next question. All right, gonna move in. All right, next question, number 6 out of 10. 5 more. Refrigerator is an example of. All right, so keep the refrigerator open and you let everything in, right? And let everything out. So it's an open system. Hey, Alexis, glad you made it. Right? So this is an open system. That's why they tell you close that refrigerator. My golly. Right? Close. It's an open system. All right. So what about this? We have energy and matter coming out. What's allowed to cross the boundaries of an open system? Here's a picture of an open system. Energy and matter. Both energy and matter are your examples here. So those are energy and matter that can in an open system, right? Energy and matter. Hey, I am happy. Who's I am happy? I'm glad you're here. Happiness. Oh, Jana, thank you very much for that. All right. So, what is allowed to cross the boundaries of an isolated system, right? Now, you don't see any arrows here that show energy or matter. So, that means neither matter or energy gets out of an isolated system. It's really hard to make, right? Right? Really hard to make. All right, so let's go here. All right, we are on 8, going to 9. 2 more questions. When we get to those. All right. Question defines a system separated the environment. So it's a boundary that separates the environment, like the cap on the top. Like an open system has no boundary, except for maybe the walls of the pot. But it's the boundary that separates those. The boundary that separates those is the way we can confine or talk about a system. And the last question here, match these up, would you please? Match these up. Let's see how you can do on these. Those pictures, match those up. Okay. So you got 3 to match. Talked about it enough, so hopefully everybody can get in there. All right. All right, so how'd we do? 49%, not too bad. Madison third, Natalia first, second, and Kendall first. Good job, ladies and gentlemen here. Thank you for coming in on this. Okay, so we are going to be talking about conservation of energy. Okay, so let me get you guys started on this, the conservation of energy. All right, hey, Leiden, how are you? Okay, so when we're talking about the conservation of energy, we're going to be talking about, oops, right here, kinetic energy, and potential energy. And that's, hey, better late than never, Leiden. Good to see you. Okay, so I'm going to start a poll here. So pick A, B, C, or D for our engage here. All right, so engage. All right, so if I told you, given an energy system, can I calculate the amount of potential energy in a kinetic energy? I have no idea what you're talking about there, Mr. Gale. I know something about what you're talking about. I know what kinetic energy and potential is. I know some. I could probably do the calculations, or can I have the test? Okay, so if you put A, that's okay. That, we're just going over. You'll get the same evaluation at the end to see how well, if you've gone up or not. Okay, so if most people are saying B and C, okay, so no most. Some people say no some. Again, trying to figure out if you know more. And again, I've never heard about potential or kinetic energy, so you would probably say, I don't know any idea what you're talking about. All right, so we got 10 out of 19. You guys are really good responders. I really could use more, to tell you the truth. All right, so energy is everywhere. We're going to be talking about the conservation of energy. And again, we're going to be talking about a hypothetical, isolated system, because it doesn't really exist in true life. Hypothetical. So we're going to be talking about that when we're talking about energy, because then that way we don't have to worry about friction or heat lost or anything like that. But did you know that your brain uses a lot of energy, changes the food energy into chemical energy, and the brain changes it to electrical energy so that you can move your muscles, talk, things like that, and even to think? Even if you weren't moving your muscles, your brain takes a lot of energy. All right, so let me show you what this looks like on the other screen here, okay, because we have a better way of looking at this when you have GIFs and links to things that are actually moving, right? So let me show you this. All right, so here's a pendulum, a weight hung by a fixed point so it can swing freely forth. So the energy of a pendulum changes as it changes position. The speed and a lot of different, and has a speed and a lot of different motion. So energy can transform or change from one type to another. So the two types of energy we have in the pendulum is gravitational potential energy, that depends on Earth's gravity and how high it is off the ground, and kinetic energy, which talks about speed of an object. All right, so speed and mass of an object. All right, so in this particular case, all right, so let me give you start a poll here. All right, A, B, C. All right, A, B, C. What point would the pendulum have the greatest kinetic energy? Motion, so kinetic energy. All right, kinetic energy, what is the one, A, B, or C? Is it the top where it has the most kinetic energy, the middle where it has most kinetic energy, or the bottom and has most kinetic energy? Right, so remember, we're talking about speed. So where do you think it's going the fastest? Right at the top there, because it kind of hesitates a little bit and goes back the other way. Or is it in the middle? Or is it the fastest at the bottom? What do you think? What do you think? All right, thanks. Hey, Brooke, good to see you. Isaac, good to see you. If you guys can get in there and vote on this, Luna, Alexis, AJ. All right. So, okay. So most of you think, all right, that it is, let me go over here. It is the top. Most of you think it's the top. It's actually the bottom, because it picks up speed as it goes. Okay. Right. So it's the bottom on this particular one. So where is the potential energy of this one? Right? Potential energy has to do with how high it is off the ground. So would you think that would be the top, the middle, or the bottom? So we talked about the kinetic energy being the fastest on the bottom as an object is falling. So pendulum is falling. So, and then it swings the other way. So it falls from a great height and then comes down, right? And so what do you think would be the most energy for kinetic? Oops. So we would win potential energy. Okay, sorry, potential energy. And you guys are right. It's the top. The height of it is the potential energy. So the top, right? And we lose potential energy as we come down. All right, so let's take a look at this video here. Will show us some motion here and also show us a graph. Okay, so far let's kind of review what we talked about. So in the greatest kinetic energy is at the bottom, right? At the bottom. And the greatest potential energy is at the top because of its height. So let's take a look at this video here. And if you look at this video, the green represents kinetic energy, the red represent potential energy, and they're both on the same graph. So right now it's showing mostly kinetic energy. So let's take a look at what happens in this particular case. Turn my pen off here and go back to pointer. All right, so here we go. Let me turn my screen off so you can see it a little bit better. So if you notice, when it gets all the way to the top, it's all potential energy. Then we lose the potential energy as we go down. Here it says no kinetic energy, all potential energy. Here it's maximum kinetic energy. All right, so let's take a look at this. We have actually added one more bar to this. And what we've done with the one more bar is we have total energy. So total energy is equal to the kinetic energy, the red bar, and the blue bar and the purple bar. Okay, so total energy is equal to kinetic plus potential, right? Hey Jay, that's great. Your 7th grade, you know, middle school teachers were, my 9th grade teacher was my best. So that is really great. So, and again, one of those things they had us have a lot of experiments we did. So let's take a look at this here. So the total energy, so here we have potential, all potential energy, no kinetic energy is stopped. Let's see if I can get this to go again. Maybe if I back up, start again. No, why not? Okay. All right, so we'll talk about this a little bit later. All right, so how energy is transformed from one thing to another. So again, in order for Tony Hawk to do all his tricks back in the day, and especially his 900 was 2.5 rotations, 360, 367, and then he did another 180. So that comes to 900. He needed a lot of potential energy at the top. So so you guys, if we could stay focused here, we don't have much time. We're running out of time here. So if we can stay focused, okay, I would really appreciate it. So keep the chat down and then you can talk things after we get done with these. So anyway, having a lot of energy at the top in order to do that, right? In order to get this going. Yeah, that's good to know, Jana. So, he has to transfer all that potential energy into kinetic energy. And if he doesn't get enough energy, he will lose it. He won't be able to do that trick. Right. So again, athletes and ourselves have to figure out how to give the energy we need in order to do things. Right. So we eat food. And again, the right food would be the best. Right. So whatever food you can eat that gives you the most energy for your muscles is important, especially if you're working out. So energy from the sun gives us plants. Cows eat the plants. We get milk, we get beef, we get all kinds of things. And when we eat that, all right, we get the energy, right? So think of the universe as a closed system, right? Where it's all contained and then the energy can leak out when it's transformed. So it's a closed system. So here's what we're going to be doing. This is what I want you to take a close look at. And this is where you're going to give me a thumbs up at the end saying that you learned something. This is the part you want to learn. Okay, so let me give you an idea here. I'm going to switch over, right, and get this here. Okay, so let's go back. Let's give us a total energy bar, right? A total energy bar here. So if you'll notice, it says at the top of the ramp, the person is not moving at all. So if we look at that, they have 0 kinetic energy. KE is 0. So here is the KE, kinetic energy, right? But they have 100% potential energy, or 100 joules of potential energy, PE. So what we do with this is straightforward. We add these two together in order to get our 100. So it says 100 joules, 100 plus 0 gives us 100, right? So that's our total energy right here. Our total energy is 100. So that's how we have all potential energy and no kinetic energy. We're not moving at all. There's no speed or motion, so we're not looking at kinetic energy at all. But the kinetic energy comes from the potential energy of the height. So here is the skater. Again, let's look at the total here. We'll get 100 joules total, right? And that is our total bar. We've lost some potential energy. We're going down the ramp. So we've got 80. Oh, is that what's happening with why you're typing there, AJ? I'm going to clear the chat a little bit, okay? All right, so we have 80 joules of energy, and we're getting some speed. We have 20 joules of kinetic energy because we're getting some speed, right? We're getting some speed, and that's what's happening. So 80 plus 20 gives us our 100 again. Remember, the total energy is 100, right? So I'm just adding these two up to get my total energy. Now we've come down the ramp, right? We've lost some of our potential energy, transforms into kinetic energy, right? We have our total energy again is still 100. The total is still 100. So let's see if it adds up here. So 60 for the potential energy because we still have some height, 40 for kinetic energy because we're gaining speed. So yeah, 60 plus 40 is 100. All right, now we've come even further and we've got more speed. So now we've got 60 for the kinetic energy, the energy there, and then 40 for potential energy. We've lost a lot more space, a lot more distance from the top. And then finally, very close, we get 20. We're almost at the bottom in potential energy. Remember, when we get to the bottom or the ground floor, we have 0 kinetic energy, 80 and 20. 80 kinetic energy because we're speeding up faster and faster. And then finally, we have 0 potential energy. We're on the ground and 100% or 100 joules at the top. Okay. So let's experiment with how that works. Okay, so I'm going to have you guys help me out with this. So let me draw some things here. Okay, so it says my total energy here and my total, change the size here to medium. Total energy, what happened to my bar here? Okay. All right, so my total energy is 25 joules. Okay, my potential energy is a small amount of energy. My potential energy, it's really close to the bottom, is only 5 joules, right? So my kinetic energy has to be add up to make 25. Okay, so what is my kinetic energy going to be? So this is my kinetic energy. It's going pretty fast. It has to add up to 25. This is my potential energy here, PE, right? All right, so what we have to do in this particular case is take my 25 and subtract the 5 that I know about, and that gives me my kinetic energy. 25 minus 5, there you go. It's pretty straightforward. If they tell you how much the total system is, it's 25. 5 joules, this has to be 20 in order for that to work, right? All right, so it has to be 20 joules. Good job, guys. Okay, one last question, and we're going to be done here. All right, so there we go. 25 minus 5 is 20 joules. Okay, so let's take a look at our total energy now. This one has a total energy now of 50 joules. Okay, so my total is 50 joules. So how we get more energy? We have more weight. We can do that. So now we have a closed system. So it has 40 joules of kinetic energy. And how many joules? So 40 joules of, oops, let's draw this out again. So let's do the kinetic energy here, 40 joules of kinetic energy, 40 KE, that's the motion part. So the potential energy, actually this is probably a little bigger than that as far as size goes. There we go. All right, 40, and then we have a little small box of potential energy, right? And so what we're going to do with this one is we're going to take the 50 joules of the total energy minus the 40 joules of kinetic energy, and that'll equal our potential energy. So what is it that you got for potential energy here? 50 minus 40, what did you get? 50 minus 40 gives you what? All right, most of you guys got it. We're not adding, we're taking 50 and we're going to try to get that 10. So we have 10 joules of PE because PE 40 plus 10 is 50. Okay. All right, so most of you guys understanding that. So let's take a look and see what, oops, so let me do this, A, B, C, or D. Do you understand this a little bit more? So if you were, this is the same thing. The system, can you calculate the amount of potential and kinetic energy? So if you were saying A, did you move over to B? Maybe need a little more practice. If you were B, you got C, I got it now. And then D, give me the answers, okay? All right, Jana. All right, so it looks like most of you guys have moved off of the publish a poll, moved off of the A altogether and no sum, at least no sum and no most. Okay, so let's practice, put this into practice. All right, so I have for you today a couple things that you can do, okay? So number one, if we look at today's assignments today, so today, week 10, all right, so let's see what we got here. Week 10. All right, next. All right, got our notes. I've got those notes posted. So there's the exit quiz from yesterday. So if you need some help with that, I'll open that big blue button, go over the exit quiz from that. All right. Hey, Cadence, you have a question for me? I'm missing it. I did not see it. Let me double check to see if you got a question here that I'm not seeing. All right. No, I don't see that. What's the question? Cadence. All right. Let me clear this out. Oop. All right. Type something in for me. I didn't see it. Okay, so yesterday's exit quiz, if you didn't do that, do it today. We are going to do the next one. All right, next one. Next one. Come on, next. All right, bonus. All right, if I get there, I will tell you. Here he is. Okay, so this is a form, Google form, but what's nice about it, it has, so this is 4.2, the exit quiz. Shouldn't take you more than 5 minutes to do this. It has some good GIFs in it to show you potential and kinetic. Also helps me to know what I need to go over. All right, so this is exit quiz 4.2. All right, so this is, so you can do that one. All right, if you want to do the 4.1, you can also do that, right? And I will be in giving you the big blue button. Hey, Cadence, you know why that happened? Is because you did all the bonus, right? You did all the bonus. That's why your grade was like that. Good for you. All right. Yeah, this is the second set of bonuses. So yeah, keep doing the bonuses and you will bring your score up for sure. Okay, so I'm going to go over, get the big blue button link. Let me turn off this video here.